Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The mid-19th century witnessed a pivotal moment in the history of physics, a period marked by a profound intellectual tension. Carnot's elegant theory of heat engines, a cornerstone of burgeoning industrial technology, rested upon a seemingly unshakable foundation, the concept of caloric, a conserved, indestructible fluid-like substance that flowed from heater to colder bodies, driving the mechanical work of steam engines. This framework, meticulously formalized mathematically by Emile Clapeyron, provided a powerful, albeit ultimately incomplete, model for understanding thermal processes. However, a different kind of understanding was emerging from the meticulous experiments of James Prescott Joule. Joule's investigations revealed the mechanical equivalent of heat, a quantitative relationship demonstrating the convertibility of mechanical work into heat, and vice versa. This implied that heat was not a conserved substance, but a form of energy itself, a concept challenging the very core of Carnot's theory. This profound dissonance, this apparent contradiction between two seemingly robust frameworks, presented a formidable challenge to the scientific community. The need for reconciliation was clear, a synthesis that would incorporate the experimental verity of Joule's findings, while preserving the essential power of Carnot's theoretical insights. Into this intellectual crucible stepped Rudolf Clausius, a figure whose contributions would fundamentally reshape our understanding of energy and its transformations. Clausius's by 150 paper on the moving force of heat and the laws regarding the nature of heat itself stands as a landmark achievement, a testament to his remarkable intellectual acuity. His approach was not simply to discard one theory in favor of the other, but to forge a new, more comprehensive framework that encompassed the strengths of both. He did this by formulating two fundamental laws, now known as the first and second laws of thermodynamics, which elegantly resolved the conflict between the caloric theory and the mechanical equivalent of heat. The first law, expressing the principle of energy conservation, directly incorporated Joule's experimental findings. Clausius rigorously established the mathematical expression du equals dQ/dW, where du represents the change in internal energy of a system, dQ the heat added to the system, and dW the work done by the system. This equation beautifully captures the essence of energy conservation. Energy is neither created nor destroyed, only transformed from one form to another. This formulation, a direct consequence of Joule's meticulous experiments, provided a quantitative framework for understanding the interplay between heat and work, a cornerstone of modern physics and engineering. However, the mere assertion of energy conservation was insufficient to fully capture the essence of thermal processes. Carnot's theory, despite its flawed foundation in caloric, contained a profound insight of the inherent directionality of heat flow. Clausius ingeniously preserved this crucial element by formulating his second law, a principle that transcended the limitations of the caloric theory. He stated it succinctly: heat cannot of itself pass from a colder to a hotter body. This seemingly simple statement encapsulates a profound truth about the universe, a truth that governs the spontaneous direction of thermal processes. It is this principle, far from being a mere assertion, that provides the arrow of time in thermodynamics. The brilliance of Clausius's work lies not only in the formulation of these two fundamental laws, but also in the rigorous mathematical framework he developed to support them. He provided a rigorous rederivation of the Carnot cycle using the principle of energy conservation and his newly formulated second law. This rederivation demonstrated that the efficiency of a Carnot engine depends solely on the temperatures of the hot and cold reservoirs, a result independent of the working substance. This finding established a new absolute temperature scale, a scale that is independent of the properties of any particular material and forms the basis of modern thermometry. This work's impact on the scientific community was immediate and profound. William Thomson, later Lord Kelvin, a prominent physicist who had previously championed a caloric-based approach to thermodynamics, immediately recognized the significance of Clausius's work. Upon reading Clausius's 150 paper, Thomson abandoned his own caloric-based theories and initiated a prolific correspondence with Clausius, a collaboration that further advanced the field of thermodynamics. The direct influence of Clausius's work on Thomson is undeniable, marking a pivotal shift in the understanding of heat and energy within the scientific community. The meticulous mathematical rigor and the elegant synthesis of seemingly contradictory ideas made Clausius's work a paradigm of scientific progress, laying the foundation for the entire field of thermodynamics and fundamentally altering the trajectory of physics. The legacy of this 150 paper continues to resonate in the countless applications of thermodynamics across science and engineering, a testament to the enduring power of Clausius's insights. The transformative impact of Clausius's 150 paper resonated deeply, yet it also revealed a significant challenge. The second law of thermodynamics, as initially formulated, functioned as an inequality, a prohibitive statement declaring what processes could never occur spontaneously. It lacked the quantitative precision needed to predict the extent to which a given process could occur or to compare the relative efficiencies of different processes. The scientific community sought a universal measure, a state function, that could quantify the transformational content inherent within a system. This measure would definitively dictate the direction of spontaneous change, allowing for precise calculations and predictions about the behavior of thermodynamic systems. Clausius addressed this fundamental problem with characteristic ingenuity, culminating in a seminal 165 paper on a modified form of the second fundamental theorem in the mechanical theory of heat. This work introduced a revolutionary concept and a corresponding term destined to reshape the landscape of physics: entropy. Deriving its name from the Greek word trope, meaning transformation, entropy provided a tangible measure of the energy dispersal within a system. Clausius's methodology involved a profound conceptual leap. He introduced the quantity ds equals dq sub reversible divided by t, where ds represents an infinitesimal change in entropy, dq sub reversible signifies an infinitesimal amount of heat transferred reversibly, and t denotes the absolute temperature. Through rigorous mathematical analysis, Clausius demonstrated that this quantity, ds, constitutes a perfect differential. This seemingly simple assertion held immense significance, as it implied that entropy, denoted by S, functions as a state function. A state function depends solely on the current state of the system, irrespective of the path taken to reach that state. This property immediately elevated entropy to a position of paramount importance in thermodynamics. providing a reliable measure of a system's inherent properties. Having defined entropy, Clausius proceeded to formulate a powerful mathematical statement known as the Clausius inequality. This inequality, expressed as the integral around a closed loop of dq divided by t is less than or equal to 0, encapsulated the essence of the second law in a quantitative form. The integral represents the sum of all infinitesimal heat transfers, dq, divided by the absolute temperature, T, for a cyclic process. For any real-world, irreversible cyclic process, Clausius proved that this integral invariably yields a negative value. Only in the idealized case of a perfectly reversible process does the integral equal 0. The implications of the Clausius inequality are profound. It provides a mathematical criterion for determining the spontaneity of a process. If, for an isolated system, the change in entropy, delta S, is positive, the process is spontaneous. If delta S equals 0, the process is reversible and a system is in equilibrium. A negative delta S would indicate a process that requires external work to occur. This led Clausius to his famous cosmological scope maxim, a concise encapsulation of the first two laws of thermodynamics. The energy of the universe is constant. The entropy of the universe tends to a maximum. This statement, imbued with grandeur, suggests that while the total energy in the cosmos remains unchanged, the universe inexorably progresses towards a state of ever-increasing disorder and uniformity. A tangible application of Clausius's work lies in his refinement of the Clausius-Clapeyron relation. This equation, a cornerstone of physical chemistry, precisely describes the pressure-temperature relationship at a phase transition, such as the boiling point of a liquid or the melting point of a solid. Clausius's improved formulation, incorporating the concept of entropy, provided a more accurate and comprehensive understanding of these phenomena, enabling scientists and engineers to predict and control phase transitions with greater precision. For instance, the accurate prediction of vapor pressure as a function of temperature is crucial in designing efficient distillation processes in the chemical industry or in understanding the behavior of refrigerants in air conditioning systems. The modern relevance of entropy is immense. It stands as a cornerstone of numerous scientific disciplines, extending far beyond classical thermodynamics. In physics, entropy plays a central role in statistical mechanics, cosmology, and information theory. In chemistry, it governs reaction equilibria and the spontaneity of chemical reactions. In engineering, entropy is essential for optimizing the efficiency of power plants, engines, and other thermodynamic devices. Furthermore, the concept of entropy has found application in information theory, where Shannon entropy provides a measure of the uncertainty or randomness associated with a random variable. This has led to profound insights in fields ranging from data compression to cryptography. Clausius's work on entropy had a direct and profound influence on subsequent generations of scientists. Josiah Willard Gibbs, a towering figure in American science, recognized the transformative potential of entropy and incorporated it as a cornerstone of his own groundbreaking work in chemical thermodynamics. Gibbs utilized entropy as a central variable in his graphical methods, which provided a powerful visual framework for understanding and predicting the behavior of complex chemical systems. In his monumental treatise on the equilibrium of heterogeneous substances, Gibbs meticulously developed a comprehensive thermodynamic theory based on entropy, laying the foundation for modern chemical engineering and material science. Gibbs's phase rule, derived from these principles, allows scientists to predict the number of phases that can coexist in equilibrium in a given system, a tool of immense practical value in fields ranging from metallurgy to geology. Ludwig Boltzmann, an Austrian physicist renowned for his contributions to statistical mechanics, was another scientist profoundly influenced by Clausius's concept of entropy. While Clausius defined entropy from a purely macroscopic, thermodynamic perspective, Boltzmann sought a microscopic explanation for this macroscopic law. Boltzmann's quest led him to develop a statistical interpretation of entropy, expressing it as S equals K times the natural logarithm of W, where S represents entropy, K is Boltzmann's constant, and W denotes the number of microscopic arrangements, or microstates, corresponding to a given macroscopic state. This equation, engraved on Boltzmann's tombstone, established a fundamental link between the macroscopic world of thermodynamics and the microscopic world of atoms and molecules. Boltzmann's work provided a statistical foundation for the second law, demonstrating that the tendency of entropy to increase reflects the natural tendency of systems to evolve towards states of higher probability. The introduction of entropy by Clausius marked a pivotal moment in the history of science. It provided a quantitative measure of irreversibility, a concept that had previously eluded precise definition. Entropy became an indispensable tool for understanding and predicting the behavior of thermodynamic systems, influencing not only physics and chemistry, but also engineering, cosmology, and information theory. The legacy of Clausius's invention continues to resonate in countless applications, a testament to the enduring power of his insights into the fundamental laws governing the universe. The concept of entropy, elegantly articulated by Clausius, provided a powerful lens through which to view the macroscopic world. Yet, the quest to understand the fundamental nature of heat demanded a descent into the microscopic realm, an exploration of the unseen world of the atoms and molecules. How could the seemingly random motions of countless particles give rise to the orderly laws of thermodynamics? This challenge spurred the development of the kinetic theory of gases, a field in which Clausius made seminal contributions. Early attempts to construct a mechanical theory of heat faced significant hurdles. August Koenig, for instance, proposed a simplified model where gas molecules were envisioned as point masses moving with constant velocities. This initial framework, while groundbreaking in its attempt to link microscopic motion to macroscopic properties, offered a limited representation of reality. It treated molecules as dimensionless entities, neglecting their finite size and the inevitable collisions that occur between them. Clausius recognized the limitations inherent in these early models. His White's 57 paper on the nature of the motion which we call heat presented a far more sophisticated and realistic picture. The innovative step was the introduction of the concept of the mean free path. This parameter represented the average distance a molecule travels before colliding with another. By acknowledging the finite size of molecules and the reality of intermolecular collisions, Clausius moved beyond the idealized point mass approximation. The mean free path became a crucial element in predicting the behavior of gases, allowing for the calculation of transport coefficients such as viscosity. This marked a significant advance, providing a theoretical framework for understanding how gases resist flow. The introduction of the mean free path allowed for quantitative predictions that could be tested experimentally, moving the kinetic theory from a qualitative description to a predictive science. For instance, the viscosity of a gas, a measure of its resistance to flow, could be calculated based on the mean free path and the average speed of the molecules. This theoretical determination of transport properties demonstrated the power of Clausius's approach and its ability to bridge the gap between the microscopic and macroscopic worlds. The problem of determining how a gas resists flow is solved by introducing a parameter that quantifies the average distance a molecule travels before its momentum is randomized by a collision. The impact of Clausius's work extended beyond the immediate problem of gas viscosity. The concept of the mean free path proved to be a crucial stepping stone for James Clerk Maxwell, who adopted it in his development of the statistical distribution of molecular velocities. Maxwell's distribution, a cornerstone of statistical mechanics, describes the probability of finding a molecule with a particular velocity in a gas at a given temperature. Maxwell built directly on Clausius's foundation, incorporating the mean free path into his more comprehensive statistical treatment. Maxwell's work directly benefited from the foundation laid by Clausius. Clausius further generalized his mechanical approach to thermodynamics with the development of the virial theorem, presented in 1870. The virial theorem provides a powerful link between the average kinetic energy of a system and the forces acting within it. Mathematically, the theorem states that the time average of the total kinetic energy, denoted as angle brackets T angle brackets, equals -1/2 times the sum of the time average of the dot product of the force and the position vector for each particle, expressed as -1/2 times the summation of angle brackets F dot or angle brackets. This seemingly simple equation has far-reaching implications, extending beyond the realm of ideal gases to encompass a wide range of physical systems. The virial theorem finds a particularly valuable application in astrophysics. It provides a method for estimating the mass of gravitationally bound systems, such as star clusters and galaxies. By measuring the velocities of the stars within a cluster and their spatial distribution, astronomers can use the virial theorem to estimate the total mass of the cluster, including the mass of dark matter, which cannot be directly observed. The theorem allows astronomers to infer the presence of unseen matter by analyzing the motion of visible objects. The power of the virial theorem lies in its ability to relate macroscopic observables, such as the average kinetic energy of a system, to the microscopic forces acting between its constituent particles. This connection is crucial for understanding the behavior of complex systems where direct measurement of all the forces involved is impossible. The theorem offers a way to circumvent this difficulty by providing a global relationship between the average kinetic energy and the overall potential energy of the system. Clausius's contributions to the kinetic theory and the development of the virial theorem represent a significant step toward providing a mechanical foundation for the laws of thermodynamics. He successfully demonstrated how the collective behavior of countless unseen molecules could give rise to macroscopic properties such as pressure, temperature, and viscosity. His work paved the way for later developments in statistical mechanics and continues to be a valuable tool for understanding the behavior of complex systems, from gases in a container to galaxies in the cosmos. Kronig's initial model served as a springboard, prompting Clausius to refine the approach significantly. The work of Clausius on kinetic theory and the virial theorem laid a strong foundation for future generations of physicists. The kinetic theory, bolstered by the virial theorem, provided a powerful framework for understanding the behavior of gases. Clausius extended these ideas to tackle more complex chemical and physical systems, venturing into the realms of electrolysis and the states of matter. These investigations demanded a shift from idealized models to accommodate the nuances of real-world phenomena. One significant challenge was elucidating the mechanism of electrical conduction in liquids, a phenomenon known as electrolysis. The prevailing theory, championed by Grauthus, proposed a chain reaction mechanism. In this view, the external electric field was considered essential for breaking molecules apart into their constituent ions. Clausius offered a strikingly different perspective in 1857. He hypothesized that a small fraction of molecules in a solution are already dissociated into charged ions due to random thermal collisions. This dissociation, he argued, occurs independently of any external electric field. The field's role, according to Clausius, is simply to direct the drift of these pre-existing ions, guiding them toward the oppositely charged electrodes. This was a bold proposition, flying in the face of established dogma. At the time, direct experimental proof supporting Clausius's dissociation hypothesis was absent. Its strength lay in its conceptual elegance and its ability to reconcile theoretical predictions with observed phenomena. Clausius's model suggested that even in the absence of an applied voltage, ions exist within a solution, poised to respond to an electrical influence. Michael Faraday's experimental laws of electrolysis served as a crucial foundation for Clausius's theoretical work. Faraday's meticulous measurements established a direct proportionality between the amount of substance produced at an electrode and the quantity of electricity passed through the electrolytic solution. These quantitative relationships demanded a theoretical explanation, and Clausius's dissociation hypothesis provided a compelling framework for understanding the underlying processes. The existence of pre-existing ions readily explained the observed proportionality, as the electric field merely facilitated the movement of these already charged species. Decades later, St. Arrhenius provided experimental validation and a detailed theory that confirmed Clausius's prescient insight. Arrhenius's work, which earned him the Nobel Prize, demonstrated that many substances, when dissolved in water, dissociate into ions to a significant extent. This discovery formed the bedrock of modern electrochemistry, confirming Clausius's earlier hypothesis and solidifying its place in the history of science. Arrhenius directly acknowledged the profound influence of Clausius's earlier work on his own investigations, recognizing the conceptual leap that Clausius had made in proposing the existence of pre-existing ions. Beyond electrolysis, Clausius also grappled with the challenge of describing the continuity of the gaseous and liquid states. This problem involved understanding how a substance could smoothly transition between these two distinct phases without undergoing a sharp, discontinuous change. He sought to develop an equation of state that could accurately model the behavior of real fluids, particularly near the critical point where the distinction between liquid and gas blurs. Johannes Dietrich van der Waals' equation of state published in 173, provided a starting point. The van der Waals equation introduced corrections to the ideal gas law to account for the finite size of molecules and the attractive forces between them. Clausius recognized the value of this approach, but sought to refine it further. He developed his own equation of state for real fluids, incorporating additional parameters to better capture the complex interactions between molecules, especially those close to the critical point. Clausius's equation, while perhaps less widely known than the van der Waals equation, represented a significant contribution to the understanding of real gases and phase transitions. It demonstrated his commitment to extending the principles of thermodynamics and kinetic theory to encompass increasingly complex systems. His approach involved a careful consideration of the intermolecular forces and their influence on the macroscopic properties of fluids. The equation illustrated his ability to translate theoretical concepts into mathematical formulations capable of predicting experimental observations. The development of an accurate equation of state for real fluids is a problem with enduring relevance. While modern computational techniques allow for highly detailed simulations of molecular interactions, equations of state remain valuable tools for engineering design and for understanding the behavior of fluids under extreme conditions. Clausius's work in this area contributed to the development of these tools and continues to inform our understanding of fluid behavior. The challenges Clausius faced in extending the kinetic theory to electrolysis and the states of matter highlight the inherent difficulties in applying idealized models to real-world systems. While the kinetic theory provided a powerful framework for understanding the behavior of ideal gases, it required significant modifications and extensions to account for the complexities of intermolecular forces, chemical reactions, and phase transitions. Clausius's work demonstrated his ability to adapt and refine theoretical concepts to address these challenges, contributing significantly to the development of physical chemistry and chemical physics. His insights into the nature of electrolytic solutions and the behavior of real fluids laid the groundwork for future advances in these fields. His exploration of electrolysis, driven by Faraday's experimental laws, led to the revolutionary concept of pre-existing ions, a concept that directly influenced Arrhenius's groundbreaking work. The exploration of real gases, building upon van der Waals' equation, further showcased Clausius's dedication to refining theoretical models to match experimental observations. These endeavors solidified his position as a pivotal figure in the advancement of thermodynamics and its application to diverse physical and chemical phenomena. He demonstrated a remarkable ability to bridge the gap between abstract theoretical principles and tangible experimental realities. Clausius's career represents a remarkable synthesis, a weaving together of macroscopic, thermodynamic principles and the nascent macroscopic world of kinetic theory. He did not view his formulation of entropy, derived from classical thermodynamics, as separate from his investigations into the behavior of molecules. He saw them as complementary facets of a single underlying physical reality. While he stopped short of the full statistical interpretation of entropy later achieved by Boltzmann and Gibbs, his work provided the essential bridge, a conceptual framework that made their breakthroughs possible. He sought to understand how the seemingly random motion of individual particles could give rise to the ordered, predictable behavior observed in macroscopic systems. This pursuit required a delicate balancing act, maintaining the rigor of thermodynamic laws while simultaneously exploring the probabilistic nature of molecular interactions. Consider, for instance, his work on the virial theorem, which provided a link between the average kinetic energy of particles in a system and the forces acting between them. This theorem, developed in the early 1970s, offered a way to calculate the pressure of a gas based on the intermolecular forces and the average kinetic energy of the molecules. The virial theorem is a direct application of the kinetic theory of gases and provided a more sophisticated model than the ideal gas law, accounting for the finite size of molecules and the attractive forces between them. This was a crucial step in understanding real gases, and it directly influenced later work by physicists such as Johannes Dietrich van der Waals, whose famous equation of state built upon Clausius's foundation. Van der Waals explicitly acknowledged Clausius's influence in his own work, stating that Clausius's investigations into the kinetic theory provided essential insights for developing a more accurate description of gas behavior. The concept of mean free path, which Clausius advanced, further illustrates his commitment to bridging the macroscopic and microscopic realms. This concept, representing the average distance a molecule travels between collisions, allowed for a more realistic picture of gas behavior than earlier models that treated molecules as point particles. By considering the frequency of collisions and the distances between them, Clausius was able to refine calculations of transport properties such as viscosity and thermal conductivity. James Clerk Maxwell, whose work on the velocity distribution of gas molecules revolutionized kinetic theory, was directly influenced by Clausius's earlier calculations of mean free path. Maxwell extended Clausius's work by providing a statistical distribution of molecular velocities, demonstrating that the velocities of molecules in a gas are not uniform, but rather follow a specific probability distribution. This work, in turn, influenced Boltzmann's development of the Boltzmann equation, which describes the statistical behavior of gases and provides a fundamental link between microscopic and macroscopic properties. Beyond his scientific contributions, Clausius's personality, marked by a fervent German nationalism, offers another lens through which to view his unwavering commitment to scientific principles. His participation in the Franco-Prussian War, where he served as an ambulance corpsman, reveals a man of deep conviction and resolute character. This same determination likely fueled his intellectual pursuits, enabling him to tackle complex problems and challenge established paradigms. His nationalism, while a product of its time, underscores his dedication to a unified vision, a desire to bring order and coherence to disparate elements, a trait mirrored in a scientific quest to unify thermodynamics and kinetic theory. His uncompromising nature is evident in his rigorous approach to defining and quantifying entropy, a concept that initially met with resistance from some of his contemporaries. Yet Clausius persevered, driven by his belief in the fundamental importance of this new physical property. Clausius's genius resided in his conceptual audacity, his ability to confront and resolve what seemed to be an insurmountable contradiction, the apparent conflict between Carnot's principle and Joule's experiments. Where others saw irreconcilable differences, Clausius forged a new synthesis, introducing the concept of entropy to reconcile these seemingly opposing views. This was no mere incremental advance. It was a fundamental shift in perspective, a recognition that energy, while conserved, could also become less available for doing work. He invented, named, and quantified entropy, transforming it from an abstract idea into a measurable physical property. His legacy extends far beyond a set of equations. Clausius established thermodynamics as a rigorous, predictive science, providing a framework for understanding energy transformations in a wide range of physical and chemical processes. He introduced the concept of the arrow of time into fundamental physics, recognizing that entropy always increases in closed systems, dictating the direction of spontaneous change. This insight had profound implications, challenging the Newtonian view of a time-reversible universe and paving the way for a deeper understanding of irreversibility in nature. He stands as the indispensable architect of the second law of thermodynamics, whose work created the essential conceptual foundation upon which Boltzmann, Gibbs, Planck, and the entire edifice of 20th century statistical and quantum mechanics was built. Boltzmann's statistical interpretation of entropy, linking it to the number of microscopic states corresponding to a given macroscopic state, would have been impossible without Clausius's prior formulation. Gibbs's development of statistical ensembles, providing a powerful framework for calculating thermodynamic properties from microscopic principles, likewise relied on Clausius's pioneering work. Even Planck's revolutionary quantization of energy, which ushered in the era of quantum mechanics, was motivated by the need to resolve inconsistencies in classical thermodynamics, inconsistencies that Clausius had first identified and attempted to address. Consider the implications of removing entropy from the lexicon of modern physics. Without Clausius's entropy, the language of modern physics would be incomplete. The ability to describe and quantify the direction of natural processes, the tendency of systems to evolve towards disorder, and the fundamental limitations on the efficiency of energy conversion would be lost. The understanding of black holes, the fate of the universe, and the very nature of time itself would be profoundly diminished. Clausius's entropy is not merely a concept, it is a cornerstone of modern scientific thought, a testament to the power of human intellect to unravel the mysteries of the universe. His work continues to inspire and inform, solidifying his place as one of the giants upon whose shoulders modern science stands. His influence extends far beyond the confines of thermodynamics, shaping our understanding of the fundamental laws governing the universe.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.